Swayam Prabha. Digital India. Educated India.
This week we have started discussing chunking, which is shallow parsing, that is short phrases from within the sentence, and the technique is conditional random field. And we understood that we need help from backup layers of NLP stack. So we'll spend some time on how morphology helps the higher layers of processing in NLP stack. So we are at the third layer of NLP stack, chunking, which is held by part-of-speech tagging, and part-of-speech tagging in turn is held by morphology. Now, the noun phrases are short noun phrases, especially are very important, non-recursive noun phrases. They're important, for example, for question answering. So many times the WH question, who, what, when, where, these kind of questions are answered by nouns and short noun phrases. What is the capital of India? Delhi. So capital of India is a short noun phrase which needs to be detected from the sentence. So let me go to discussion on morphology. We started this discussion yesterday. Is everybody seeing the screen? What is morphology?
Yes, sir.
Yeah, and some student, please.
Yes, sir.
Okay. So morphology is the study of words, and it breaks the words into its parts. So washing becomes wash and ing. Bats is actually bat plus s. But morphology formation has complexities. So it is not always the case that the morphology happens in the same uniform way. So bat becomes bats, rat becomes rats, boy becomes boys, toy becomes toys, fine. But why does lady become ladies? L-A-D-Y. Why does it become ladies? Body become bodies. Why? Okay. So this is a question of what is called morphology paradigms. So though boy and lady both are ending in Y, they follow different morphological rules, word transformation rules. So they fall in different paradigms. So now a word form is composed out of morphemes, and morphemes have independent grammatical function. So this we understood yesterday with the word reconsideration. And you can have really long words, not so much in English, but in Hungarian, Polish, Tamil, even Marathi, Manipuri. There you can have very long strings composed out of words and morphemes. Morphemes have grammatical role. So we understood yesterday that the word reconsideration is composed of consider, which is the root or the stem, and Asian is a morpheme again. Its purpose is to transform a verb into a noun. Okay, so Asian, shun, their role is to convert a verb into noun, and re indicates repetition. So this kind of very definite roles are associated with morphemes. So morphemes have grammatical. So what I was saying is that reconsideration, consider is the stem. Re has the role of repetition, indicating repetition. Asian and shun, they have the role of converting a verb into noun. So then we understood that these have grammatical rules. The difference between morpheme and character. Character is smaller than morpheme. So characters have what are called lexical roles. Okay, they occupy position of single byte, let's say, in terms of computing terminology. And so morphemes are composed out of characters, but morphemes have grammatical role. Characters don't have grammatical role. Okay, and bigger than morphemes are syllables, which have pronunciation role. Bigger than syllable is the word, which has semantic role. Bigger than word is phrase, which has syntactic semantic role. Bigger than phrase is a sentence, which has syntactic semantic pragmatic role. So this way, more and more complexity is created from smaller to bigger pieces. Okay, so what I said is that from character to morpheme to syllable to phrase to sentence to paragraph to chapter to book, you have bigger and bigger units of text created, and the meaning, semantics, pragmatics, all these forces, okay, begin coming and emanating from these pieces of text. Okay, so as we build a bigger and bigger text unit, more and more functionalities appear. Of course, along with ambiguity. So now, the reason for studying morphology, we have discussed to an extent. One from the point of view of machine learning and data, another from the point of view of linguistics and theory. Okay, one point of view is data and machine learning. The other point of view is theory and linguistics and language phenomenon. Both motivations are very interesting, and they have driven research, development, and thinking and reflection. So now there is a compelling reason for looking at morphology, because data doesn't come cheap. Okay, you have to invest in money, energy, manpower, time to create data and also to annotate the data. So we showed very convincingly through our work that if we apply even simple morphology, then a higher level NLP task gets tremendous help. So we showed that with about 50,000 words in the training data, we have an accuracy of close to 80% for part of speech tagging in Marathi. But even with very weak morphology, just break the word into two parts, its stem and the suffix. Even with that, we can achieve an accuracy of 85% for the same amount of data. And if we use rich morphology, I'll explain what is rich morphology, then the accuracy jumps to above 90%. So this is a very compelling reason, and it is not typical of Marathi only. This has been observed across languages. Languages which are rich in morphology, rich and poor, I'll explain very soon. They should exploit morphological features and bring that richness into computation. It will be foolish for them to ignore the richness that they have in the morphology. Same thing is the case for chunking and for different parts of speech like verb, non-verb, and so on. So this was a good evidence. It's from one of the Indian languages, came from our lab, that morphological processing helps in computation by reducing the data. And if you have large amount of data, then morphological processing will push the accuracy up further. So just making sure that you are looking at a graph. Some student, can you please verify you're looking at a graph?
Yes. Yes.
Okay, fine. So now rich morphology and poor morphology. Languages are, they fall in a spectrum starting from very poor morphology, which is like Chinese, to very rich morphology, which is, let's say, Hungarian Arabic. And in our country, Tibeto-Burman languages like Manipuri, Garo, and Tamil. And weak morphology in our country is Bengali, Assamese, and so on. But they're still richer than English morphology. Now, I thought of an analogy to convey this idea of richness in morphology or poverty in morphology. So everybody sees a picture here of people dressed in coat, pant, and so on. Can somebody verify?
Yes, sir.
Yes, sir.
Okay. So you see here a male person dressed in a different attire for different occasions. So first is white tie, second black tie optional, semi-formal or business, business casual, casual, ultra casual, and sloppy. Okay, so these are different situations, and maybe the same individual is dressing differently for different occasions. So for very casual situation, the last dress sloppy, an extremely formal situation, maybe meeting the governor, the white tie dress. Okay, so clearly this person is rich. He has many dresses for different occasions. Maybe he dresses for lunch, dinner, breakfast also, because the situation is different. So I can look upon the stem of a word as the bare word, and on that suffixes, affixes, prefixes, infixes appear. They are like clothings, and they create different word forms. So a very good example of that is the verb conjugation. Verb conjugation means transformation of a root verb into different forms. Now the verb transforms for primarily 6 factors: gender, number, person, tense, aspect, modality. Gender, male, female; number, plural, singular. Sanskrit has dual also. Person, first, second, third person, I, you, and he. Tense, future, past, and present tense. Aspect, continuous aspect, going. Modality is imperative, declarative, question, interrogative, that is exclamatory, and so on. So modality, you go, you please go. So that is a request. Okay. So for these 6 factors, almost universally all verbs change their form depending on how rich the language is with respect to morphology. So these situations are like lunch, dinner, breakfast, or meeting the governor, or going to the sea beach. All these factors are situations for us. So if I take the root word jana, it transforms to jaunga, jaoge, jayenge, etc. And a tree here is relevant. This is called morphology tree. So I'm discussing, I'm investigating, let's say, the jana verb for future tense. So first line of division is gender, male, female. Okay. Then under each gender, second line of division is number, singular, plural. Under female again, singular, plural. Third line of division is under each number, first person, second person, third person. So after below that it will be aspect. Below that it will be modality. Okay. So this way a tree will develop starting from the root, which is nothing but the stem or root of the word. So jana is the stem or the root word. So jana gets transformed for masculine gender, singular number, first person, or masculine gender, singular number, second person, or third person, and so on. Okay, so you can see that first level has 2 children, second level has 2 into 2, 4 children, third level has 4 into 3, 12 children, fourth level has 12 into the number of modalities, then the next level has into the number of aspects. So this is called a morphology tree. Okay, and if you follow a path from the root to the leaf, okay, in this case the tree is not developed for all levels. We are considering only gender, number, and person, G and P. Here jana has become jaunga. So for male gender, singular number, and first person, jaunga, I will go, मैं जाऊंगा. Male, singular number, second person, तुम जाओगे, you will go. Male, singular number third person, he will go, वो जाएगा. So जाऊंगा, जाओगे, जाएगा. So for Hindi, you can see that all the three leaves have different forms. These are for three different situations. So the word jana has dressed itself for these three different occasions. Okay, but compare with English. English has for all these three, jaunga, jaoge, jaega. For all these three forms, English has a single transformation: will go, will and go. Okay, and also note that the auxiliary will is different from go. There is a space between will and go. Okay, so auxiliary verb is separate from the main verb go. But in case of Hindi, the suffix indicating gender, number, and person is attached to the word. Okay, attached to the word. So English has what is called isolating morphology. Isolating morphology. That means the morphological information is typically isolated from the word form. So go is the root form of going activity. The gender, number, tense, person will be separately indicated by auxiliary verb. Okay, that's why it is called auxiliary or helping verb. On the other hand, the gender, number, person for Hindi is indicated by a suffix sitting on the verb. So this phenomenon is called inflection. Okay, inflection and isolating. I'll put it on the slide. Inflection morphology and isolating morphology. More complex than this is agglutinative morphology, which happens in Tamil, Manipuri, in India, and in Europe, Hungarian, Polish, and so on, in Asia, Arabic, Turkish, and so on. Okay, so these are different processes of morphology which apply on the root word. Okay, I'm sure people would have questions on this. Please put them on the chat box for me to answer after some time. Now, why are we discussing all this? We are discussing all this because these are very valuable considerations for higher level of natural language processing. In particular, they are very helpful for data sparsity. So let me give you an intuitive example. Suppose in the training data, you have seen jaunga, but you have not seen khaunga. Okay, you have not seen khaunga. So then in the test sentence, you have seen khaunga. Can you do any NLP on khaunga? You can, because you have seen jaunga and you could separate unga from jaunga. And unga is an indicative of future tense, masculine gender, singular number, and first person. Okay, these are important features. So these features will tell the classifier or the sequence leveler that give it the verb tag, and going further higher up, make it a part of the verb phrase, the verb chunk. Okay, so these features immediately indicate that this is what you can do. You don't need too much data for this. Okay, so this is the motivation for studying morphology, because words contain valuable information for subsequent natural language tasks. And I think it will help you to remember this analogy with dressing for different occasions. The morphological transformation on the root word is like clothing on the body for different occasions. So the clothings on the word are different kinds of affixes, namely prefix, infix, and suffix. Okay, so this is a very important discussion, because we are dealing with the elementary units of text, which is word. So there are more interesting facts about morphemes and morphology. So lovely is an adjective. Ly is the suffix for this. Quickly is an adverb. Li is again the suffix. So lovely is adjective, quickly is adverb. Why so? A little bit of explanation is possible. Even though the suffix is same, the stem word in its natural usage is a noun for adjective formation and adjective for adverb formation. So li, when sitting on an adjective, makes it adverb. Li, when sitting on a noun, makes it an adjective. Okay, so that's a very definite grammatical function that the Lee morpheme has. Okay, but both of them indicate manner of or state of, which is the semantics of Lee. Now, the basic classification of English morphemes is shown on the screen. So we're looking at basic classification of English morphemes. So morphemes can be free or bound. Okay, free morphemes have independent bases. They can exist independently in a piece of text. So all dictionary words are free morphemes. Okay, morpheme need not be only word parts. Words also are morphemes, but they're free. They can exist independently. Tree, go, fat, etc. Bound morphemes are those which have attached with a free morpheme to give another free morpheme. So a very important kind of bound morpheme is affixes. Affixes can be prefixes, suffixes, and even infixes. So prefixes are like the word post, the morpheme post. So when you say postpone, then post is the bound morpheme which attaches to another morpheme to give an indication of deferring something, okay, pushing it forward in the time line. This is prefix. There are many prefixes like un, for example, unjustified. Un indicates no. Unsuitable, yeah, not suitable. So un is a prefix. Similarly, in is a prefix. Suffixes are the morphemes which attach to the end of another morpheme. So tossed, for example, walked, envied, ed. So ed is a suffix which indicates past tense of a verb. So you have prefixes, suffixes. Other kind of bound morphemes are bound bases. For example, cran. So from cran you can get cranberry. So but cran doesn't have the kind of grammatical role that prefixes and suffixes have. Okay, or we have contracted form like they will. You write it as they and then this upper quote and double L. Okay, so this the quote and double L, that is a bound morpheme. It doesn't have independent existence. It has to attach to words like we, you, they, and so on. Okay, so this is a classification of morphemes, and an understanding of this kind of classification helps us design better NLP algorithms, and in particular doing feature engineering for classical machine learning, or enriching the input layer of the neural network with features when we are doing an NLP task. Both in deep learning and in classical machine learning, this kind of knowledge of features and properties is very helpful. So just one more time, because this is universal, this tree is universal across languages. Morphemes can be free or bound. Free morphemes are words. Bound morphemes are affixes, bound bases, and contracted forms. Affixes probably are more important for us, very important for us. Affixes can be prefixes, suffixes, and even infixes. I'll show an example. And bound bases are like cranberry. Contracted forms are like they will, where you have quote and will. Another example of contracted form will be don't. Do not is D-O-N apostrophe T. So N apostrophe T is a contracted form. Okay, so this happens in English, and it will be interesting and very instructive for you to draw a morpheme tree for your own language. Okay, your own mother tongue. The Hindi speakers can draw this morpheme tree for Hindi. Assamese speakers can draw for Assamese. Telugu speakers, Tamil speakers, Manipuri speakers, Khasi speakers, please draw the morpheme tree for your own language. And also give examples at the leaf node. The same tree will apply. You just have to fill the leaf node from your own language. So TA team, please put this as an exercise. Okay, draw the morpheme tree for your own language, for your mother tongue. Draw the morpheme tree for your mother tongue. In future, when you do natural language processing for Indian language, for example, you are doing sentiment analysis for Gujarati, or you are doing question answering, let's say for Bhojpuri, okay, or you are doing machine translation for Kashmiri, okay, you will remember that once Sir had asked me to draw the morpheme tree for my language because I am now called to create a natural language processing system for my own language. Okay, so that is the relevance looking into future. Now, please do this exercise, and TA team, please put this as an exercise. Now, besides prefix and suffix, you have infix also. Infixes are strings which sit inside a word. So there is a language called Bonto Igorot. Okay, there are many languages in the world. There are about 6,000 to 7,000 languages, and there are many dialects. Okay, Bengali, for example, has many dialects, and interesting and well-known dialect is Sylheti, which is a region now falling in Bangladesh. Okay, so Bonto Igorot, I think, is a language in Africa, and there is an interesting morphological phenomenon. You have the original word Kayu, K-A-Y-U. Inside that, you separate K from IU and insert in, I-N. Then you get a complex word, it is Kinayu. So Kayu is wood and Kinayu means gathered wood. See, so much of semantics is packed into the word by an infix. So Kayu becomes Kinayu, so wood becomes gathered wood. So this is an example of what is called derivational morphology. We'll talk about that. In Sanskrit, you have an interesting example, Rajayate. Rajayate means to behave like a king. So Raja is the stem word and te is a suffix indicating a verb. Okay, te is does. So inside that you insert the infix ya. So Raja ya te. So this means behave like a king. And this is very productive. You can attach it to many nouns. For example, you can have Drumayate, behaves like a tree. Okay. So you can take a huge number of nouns and do this ya and te and form a verb out of this. So this is an example of infix, and infix is also a kind of morphological transformation, not as frequent as prefix and suffix, but it is not unheard of for many languages of the world. So morphology and grammatical categories, nouns, verbs, adjectives, adverbs, they have different grammatical operations. For example, nouns inflect for number. Adjectives in English don't inflect for number, but they do inflect for many languages, including Hindi. In Hindi also, the adjectives inflect. For example, Sundar Balak, Sundari Balika. Okay, in Sanskrit also this happens. So this kind of transformation is seen in South Indian languages, Dravidian languages quite a lot. Verbs inflect for tense. Nouns do not inflect for tense, at least in English. So boy, the boy laughs, the boy laughed. Okay, you do not transform the word boy because the tense has changed from present tense to past tense. So these kind of transformations happen, and we will go on dealing with morphological discussion for a few more classes. But let me go to the computational part. I mean, what do I do with all this morphological knowledge, and how do I make use of them for NLP task? So let me go into the chunking problem, which we started discussing yesterday. Okay, there are very interesting recent developments in morphology, fast text, for example. And then our work on pre-trained embedding for Indian languages. I started mentioning them yesterday, but I'll elaborate later. Joint model for embedding and morphology. Byte pair encoding is such an important point, again, from the point of view of morphology. But let me go to chunking, because chunks are targets for, let's say, question answering, or feeders into question answering. So he reckons the current account deficit will narrow to only 1.8 billion in September. So please verify that you're looking at data example for chunking. He reckons the current account deficit will narrow to only 1.8 billion in September. So he is a noun phrase, reckons is a verb phrase, NP, VP, they stand for phrases. They will again meet us when we discuss parsing. The current account deficit is a longer noun phrase. Will narrow is a longer verb phrase compared to reckons. Preposition phrase is to, and again noun phrase only 1.8 billion. Another preposition phrase in, another noun phrase September. Okay, so these are NPs, VPs, PPs, etc. But they will be dealt with more elaborately in more detail when we do parsing. Now, he is a personal pronoun. Part of speech is telling me that. Reckons is third person singular number, present tense verb. The is a determiner. Current is an adjective. Account is a noun. Deficit is noun. Will is a modal. Narrow is a verb in base form. To is preposition to, indicated by to. Only is adverb indicated by RB. Hash symbol, 1.8 is cardinal. Billion is cardinal. In is in preposition. September is NNP proper noun. So the part of speech tagging phase is over. We have really dealt with a complex task, part of speech tagging. Now there is an easier task. We have to group the non-recursive noun phrases, okay, short noun phrases. He is a noun phrase and it is B. B means he begins that noun phrase, short noun phrase. Then reckons is B and VP. This means reckons begins a verb phrase. Now he was beginning a noun phrase. Where is its end? Where is the end? One is naturally asking. Where is the end of this? Okay, its end comes when another B appears. Okay, so a chunk which begins with B goes up to that position before the next B. So he is a one-member chunk. Reckons begins a chunk. Where does it end? It ends before the next B. The next B begins here, the, and then B, I. Beginning inside, inside, inside. So the current account deficit is a 4-word chunk, and current account and deficit are inside that chunk. Where does the chunk end? That chunk ends just before the next B. Well, it begins with will and then an I, therefore narrow. Will narrow. Will narrow is a verb chunk. The current account deficit is a noun chunk. To is the next B, so the verb chunk has ended with narrow. Only is RB, again a B, so to is a single word chunk. Only is beginning a chunk, but how long is that chunk? You go up to the next B. So I start going B, I. So I see that this is a 4-word chunk. Only hash 1.8 billion. So this 4-word, and in is B. September is B. Okay, so let's understand this carefully, and it is an important point that in chunking, I am dealing with only 2 levels, B and I. So it's a much simpler problem compared to pause tagging, because you have only 2 classes, B and I. And for every position, I just decide whether that position is beginning a chunk or is it inside a chunk. I don't have to decide whether the chunk has ended, because the next B will indicate that. So, so this is the way things are chunked, and the chunks are targets for simple questions. So if I ask what will narrow, then the answer is the current account deficit. So the question answering system will focus on this noun phrase, the current account deficit. Okay. If I ask when will it narrow, then again a short noun phrase, September. Okay, September. Who reckons? He reckons. He could be, let's say, the economist. So you see the importance of short phrases, short noun phrases. They are very, very important in NLP, and we should get these chunks or short phrases with high accuracy. So that's why we have to pay attention to technique for chunking. And for this, the technique which has been found very useful is the conditional random fill. It has achieved spectacular success. More than 95% is routine, and you get very close to almost 100% accuracy on short noun phrase. So this I would call a triumph for machine learning based NLP. While parsing has done very deep study of syntactic analysis based on grammar, and that makes use of heavy duty linguistics, chunking on the other hand is more towards machine learning, and it has been a favorite problem for people dealing with NLP and machine learning, or application of machine learning to NLP. And it turns out that there is a nice sophisticated algorithm for doing this task. So we started discussing the technique for this, and this is the mathematics of chunking. So again, the appeal is to noisy channel, and the task is very clear. We have a string of words. This is a Marathi sentence, Mansane Urण्याचा Prayatna Kela. So this is a 4-word Marathi sentence. The noun, the tags are noun, gerundial verb, noun, and past tense verb. Noun, VG, NN, VG, NN, VVD. And the chunks are very simple, B, B, BI. So BI indicates a chunk of 2 words, and these 2 B's indicate 2 chunks of single word each. Notice that we are solving an easier problem, only giving the beginning and length of the continuation of the chunk. If we are asked to put also the levels, what kind of chunk is this? This is a noun chunk. This is a gerundial verb chunk. This is a verb chunk, prayatna kela. Okay, so then the task is little more complex because you have to give the levels. Okay, so this is a much simpler task, and we look at the mathematics. The mathematics is not very different from what we did for part-of-speech tagging, except for one crucial difference. We do not apply the Bayes rule. So the screen you are seeing is decoding for the best chunk. Decoding for the best chunk. Please verify that you are seeing this. Decoding for the best chunk.
Yes, sir.
Okay. What about Jyotsna? Jyotsna, did you say yes?
Yes, sir.
Yes.
Okay. Some student, please. Decoding for the best chunk.
Yes, sir.
Okay. So the mathematics is very similar to what we did for part-of-speech tagging, and there is no surprise there. Part-of-speech tagging, chunking, all these are sequence leveling tasks, including parsing, as you will see. So though one wonders how can chunking be a sequence leveling task? After all, you are grouping things. I understand part-of-speech tagging is a sequence leveling task. How can chunking be a sequence leveling task? So there is a bit of ingenuity because of the introduction of the BIO notation. Okay, begin, inside, outside. Now outside is redundant because only B and I is sufficient. So that I will call is a very nice innovation on the part of NLP researchers. The task of grouping is converted to the task of sequence leveling, you see, because of this nice way of labeling things and the notion of begin and inside. So B and a string of BI will be the levels. So the best possible level sequence, chunk level sequence is obtained by argmaxing on Y given X. X is the observation sequence, Y is the level sequence. So in this case, X is the sentence, and we assume that the sentence has been post tagged, and we assume that the sentence's words have been morphologically processed. So the parts of the words, properties of the words or features, and the position of the words, and previous words tags, all these information are available to us. I know, for example, that the word is ending in li or shun or ed. All this information is available to us. Okay. So now, what feature to use and what not to use is a matter of empiricism. It is a matter of experimental judgment. You will have to use features and see what is the behavior of the classifier, what is the accuracy of the classifier or the sequence leveler. So feature engineering is a matter of design decision. It is a function of the experimental maturity. A lot of trial and error goes into it. But a few things are accepted. Okay, suffix and stem. If you separate the word into suffixes and the stem, that is a useful thing to do. If you take the part of speech tag of the word for chunking, very useful. If you take the part of speech tag of the previous word and the chunk level of the previous word, this is also useful. Okay, so all these are understood to be useful. When you are at the level of part of speech tagging, you should separate the word into suffixes and the stem, prefix and the stem. You should do that. This is useful, and also the previous tag, etc., are coming as useful information. So now argmax, probability of y given x. What is lambda doing? Lambda is the all-important weight vector. Okay, so the whole thing is feature driven, and which feature gets how much of importance is decided by lambda. Okay, so
sorry to interrupt, sir, but time for
yeah.
questions, I guess.
Oh, time for question. Yes, another 1 minute. So let me just give the intuition and develop the whole mathematics properly on Thursday. So this y given x is modeled as lambda dot f y comma x, and the probability of y given x is e to the power lambda f y x divided by z lambda x. So essentially what you're doing is that you are taking the weighted values of the features. The features are made numerical. For example, if Shran is present, the value is 1. If it is not present, value is 0. So all these features are multiplied by weights and raised to the power e divided by summation of e to the power this weighted feature vector combination. So that makes it a probability function. Okay, so this is your probability modeling, and the training based on the data is essentially finding out these weight values. Okay, so this is the main idea, and you can see that Viterbi can be applied because this probability of y given x can be converted into product of probability of yi given y minus 1 and x. Okay, so you can get the transition probability of the next state given the previous state and the input information. So since you have the transition probability, Viterbi can be applied on the search tree that you create starting from the start state. So the problem is not at all different from part of speech tagging. You start with hat, go up to dot, and find out the best possible path, which is the best possible chunk sequence, the BI sequence. Okay, so as Dipesh said, I'll take the questions here for the remaining 10 minutes.
Right, sir. The first question is by Kartavya. So in the hierarchy you were talking about where you talked about morphemes and words and then up to sentences and books. He asks, in this hierarchy, is the parent a superset of child always?
Parent is superset of child always. So bound morphemes, yes, that's right. So affixes are subset of bound morphemes because bound morphemes consist of affixes, bound bases, and contracted forms. Yes, that's true.
The next question
Hello,
is by...
sir. Sorry
Yeah,
to interrupt. Sir, I was
yeah.
talking about the hierarchy in which you said that different levels of NLP, like there's morphemes, then there come the syllables, then there comes the chunks, that
Oh,
hierarchy.
oh, that hierarchy. Okay. So you have character, morpheme, syllable, word, phrase, sentence, paragraph, chapter, right? Is that what you're referring to?
Yes, sir.
Yes, sir.
Yes.
So mainly
then,
morphemes and the syllables.
no, I didn't understand the question. Ask again.
So maybe I have a doubt in that, as you said, the syllables or the sentence subwords which contribute to the sound of a particular sentence, the
Mm.
different syllables, are
Mm.
morphemes a smaller subunit and strictly contained within the different syllables, or the other way around?
Okay, I understand. So, I think your question is, uh, of course, a syllable is made out of morphemes. So maybe your question is, can morphemes straddle syllable boundary? Is it possible that you build a morpheme by taking the end part of a syllable and the beginning part of the next syllable? Is that your question?
Yes, that fits well. Yeah.
That is the question. Yes. No, morphemes cannot straddle syllable boundary. Syllables are composed out of morphemes, and when new syllables begin, new morphemes start that syllable. So let us take unpredictability. Let us take the word unpredictability. Okay. So now here, what are the morphemes? Unpredict, a ability. Okay. Unpredict, able, et. These are the morphemes. Now the syllables are unpredict. Predict itself is composed of two morphemes, pre and dict, two syllables rather, pre and dict. Okay, so the syllables will, because predict also is composed of two morphemes, so pre and dict. Okay, so there is a root dict which can be traced to Latin, and pre is coming as a prefix for that Latin stem. So so yes, the morphemes cannot straddle the syllable boundaries.
So the next question is by Vishal. His question is from yesterday's topic, and he asks, "What is the difference between phrase and chunk?"
Phrase and chunk. Okay, so so the phrases are recursive. So the example that I gave was, the boy who lives in Delhi is coming tomorrow. The boy who lives in Delhi is coming tomorrow. Now the boy who lives in Delhi is a phrase. It is not a chunk, because who lives in Delhi is another clause, okay, which is a phrase, and clause is a kind of phrase actually. So the whole phrase, the boy who lives in Delhi, contains another phrase, who lives in Delhi. So that's not allowed in chunk. In chunk, you have a sequence of words which is non-recursive. So the boy will be a chunk here. Delhi will be another chunk. Okay, lives in, there again single word chunks. Who is also a chunk. Okay, so so yes, so chunks do not allow other chunks or phrases within them.
Sir, the next two questions are by me. So the first one was, does a rich morphological feature set always help improve downstream NLP tasks? But I think you answered this question already. We may choose to use different features, and it's more like a design choice. And the other one was, do all languages have gender roles assigned to words?
No, no. So Sita khati hai, Ram khata hai. Bengali Sita khaye,
Yeah,
Ram khaye.
I asked these questions for the benefit of the class, sir.
Yeah.
So the next question is by Nimesh. So can a rich morphological language lead to higher time complexity in parsing phase? And I answered this by saying a language can have richer morphological feature set, but time complexity will primarily also depend on which of those you use for learning what word properties. If you use a larger feature set, yes, complexity will surely increase.
Yeah, so I think this should be answered uh, with two things in mind. Okay, so time complexity of training or time complexity of testing. Okay, so let us discuss both. Time complexity of decoding versus time complexity of training. Okay, so now decoding is let's say if I take beam search or Viterbi, let's take Viterbi. Viterbi is linear complexity in terms of the length of the sentence. Okay, it is linear in the length of the sentence, and since all the probabilities have been already encoded, okay, they're already stored. Therefore, Viterbi will continue to remain linear, whatever be the number of features. Okay, the testing complexity will remain linear. Training complexity, on the other hand, will increase with features. So this we have to discuss when we discuss conditional random field, because e to the power lambda f, you have a weighted vector of, we have a weighted sum of weight vectors and the feature vectors. As the number of features increases, the vector length also increases, and you have to perform more addition operations. Okay, and depending on the number of features, the time complexity of training increases. There is a gradient descent kind of algorithm for training the conditional random field, gradient descent kind of algorithm. Okay, and that complexity goes on increasing very rapidly as the number of features increases. So who asked this question?
This was Aditya Anil Jain. Oh no,
Aditya,
sorry. This was Nimesh Agrawal.
Nimesh. So Nimesh, did I answer your question?
Yes, sir. Am I audible?
Yeah, you're audible.
Yes, sir.
So a follow-up question on this.
Yeah.
I asked this question from the perspective of real-time applications.
Yes.
So in real-time applications, might it be possible to, to subtract some features to give a better time complexity or better output in real time?
Okay, so all these are actually balancing acts. These are trade-offs, okay, between accuracy and the resources that you have. So you can really achieve high accuracy, but the investment in time and resource would be tremendous, and you may not be happy with the return on investment. The other problem is that as you introduce more and more features, that is more and more information. And information always comes with a peculiar property. More information is not necessarily better. Okay, because this information can come with its own noise and ambiguity. Okay, so more information can also be misleading. So this many of these examples we will see throughout the course. So introducing more features may push the accuracy up, but the investment in resource may not be commensurate. Also, accuracy may not always go up, especially at higher levels of natural language processing, where you will see that more information also introduces topic drift.
Next question is by Aditya Anil Jain. Sir, after breaking the dataset into morphemes, how do we track back to get to know which exact words the morphemes map to? For example, jaunga and khaunga. Once we get unga as a match, how do we get to know whether this occurrence corresponds to which of the above two words in the original data?
Yes, good question. So when we deal with subwords, this is called subword NLP, subword computation. When we deal with subword, then yes, rejoining and synthesizing the target is a challenge. So in our lab, we have a very interesting example. I think Tamali found it. Kajal, the eye ointment which you apply, Kajal was broken up by byte pair encoding into Ka and Jal. Okay, Ka and Jal. Now on translation, Ka became off and Jal became water. Okay, so this breakage was forced by byte pair encoding because Ka is frequent, Jal is also frequent. So these are good candidates for substrings. So in the translation, of course, the things became wrong because this independent translation of the two units was not desirable. So here also, I'm not answering your question directly. You are right that tracing the suffixes back to the original word is a challenge. It is indeed so, and in machine translation.
Yes, sir. Aditya here. May I?
Yeah. Yeah, please.
Yes, sir. So the question exactly aims to ask as the purpose is to get the maximum possible length morpheme mapping, right? As you mentioned, Kajal. So it's always better to map Kajal and not Ka and Jal separately. So what can be done to remember from what parent this morpheme came from, so that we can track back and get the largest possible morpheme at the end?
Parent would mean what? What exactly is parent?
So for Jauga, when we get Uga word, so we can look for parent. Like parent was Jaunga, the complete word from which. So if Uga matched, then I'll look for Jaunga, and if Jaunga matched, then it would be better to consider Jauga, because that's the word we were looking for.
No, the situation that I presented was I have not seen Khaunga, and it came in the test corpus, test sentence. But because of Unga, I am still able to give the part of speech tag of verb to Khaunga, and also say that this is future tense, first person singular number and future tense because of Unga. Okay, and there I don't see why I should go back to Jaunga.
Okay, yeah, yes, sir. So the situation was very specific, but I got it. Yes. Thank you, sir.
Okay. Yeah.